Story time! When I was a child, I almost drowned twice. Once was just in a swimming pool. I just decided to walk into the deep end. That was silly of me. The other time was when I was at Sandcastle. I went down a water slide and couldn't find my way up. Water's dangerous. But anyways, at an amusement park, a swimmer uses a water slide to enter the main pool. These water slides are super fun. Like, I'll never not stop using water slides. They're so much fun, even with the risks. But if this swimmer starts with an initial speed of 0.84 meters per second, because you kind of like use the bar to kind of swing yourself in, and then they slide without friction, because, you know, the water's like making everything all nice and slick, and they fall through a vertical height of 2.6 meters, or 2.61 meters, what's her speed at the bottom of the slide? So let's draw ourselves a little picture here, and then see if we can work this out. So here's our slide, and it really doesn't matter the shape of the slide at all. It doesn't matter if this slide is long. It doesn't matter if the slide is straight down. The only thing that matters is that from the top to the bottom of the slide, that vertical distance there in every case is 2.61 meters. So even if this slide here has some curves, as long as this top to bottom distance is 2.61 meters, the actual path of the slide doesn't matter. Heck, you could even make a slide that does something like this. But as long as from the top to the bottom is 2.61 meters, the shape of the slide doesn't matter for conservative forces. If there's friction, things change. But in this case, there is no friction, none of that matters. Okay? So that's a very important thing to keep in mind just before we kind of tackle into this problem. The path doesn't matter for conservative forces. All that matters is where you start and where you finish. So, in this problem, she is starting at the top. She's ending at the bottom. Let's see how this goes. Well, in this problem, we know we have some initial speeds, so that's initial kinetic energies. And we know that we're starting at some height, which means that there's probably a gravitational potential energy in this problem as well. And we're looking for a speed at the bottom, so that means there's some sort of kinetic at the bottom. There's no springs, though, so let's just ignore springs. So if we write out our conservation equation, we're going to have a 1/2 mv squared plus an mgh equal a 1/2 m final velocity squared, or v prime if you want to, plus mg, and then the final position for h. Maybe I'll call these initials back here. Now, with these potential energies, we've seen this before. These heights are measured relative to some position, and we pick that position. That's something that we need to make a decision about. It is often a clever move to either pick the initial or the final point as the reference position. In this case, because we're looking for a final velocity, let's make this final position down here the reference. Because if that's our reference, then when she reaches the bottom, her final potential energy becomes 0, and it goes away, because we've reached that reference position. Because of this, we know that the only h value we have is going to be 2.61 meters, and that'll be positive because she has that stored energy. So in this case, if we go ahead and kind of write this out again, we're going to have a 1/2 m, and we don't know her mass, so let's just leave this as m for a second. But then we do have some things here. We know her initial velocity, 0.84 squared, plus some unknown m, times 9.8, times her initial height, that's the 2.61 meters. And this is going to be equal to 1/2 m, which we still don't know, times this final velocity squared. Oftentimes in physics, if you're not given a mass, it's for a specific reason. And the reason often is that the mass doesn't matter. Notice how the mass appears in every term here. And since that mass is in every term, it will divide itself out, or it will cancel out. So we actually do not need this swimmer's mass. It doesn't matter. And that's a really weird thing to think about, because maybe you're thinking, oh, if they have less mass, maybe they'll go faster at the bottom of the slide. Or if they have more mass, they'll go faster at the bottom of the slide. It doesn't matter. They'll go the same speed at the bottom of the slide, assuming only conservative forces. Okay? So the mass doesn't matter here, which means our equation can simply be written as 1/2 of 0.84 squared plus 9.8 times 2.61 equals 1/2 times VF squared. And at this point, we are just shoving in numbers to solve this problem out. Let's get that 0.84 squared. That's 0.7056, and then divide that by 2. So we get let's just say 0.35. 9.8 times 2.61. Let's just call that 25.58. And equals 1/2 VF squared. Now we're just walking through the math. Let's combine these terms here. 25.58 plus 0.35 is going to give us 25.93 equals 1/2 VF squared. We've got to get rid of that 1/2, so let's multiply by 2. So we now have 51.86 equals the final velocity squared. And as we've seen many times before, if we want to get rid of this square, we take a square root. Square root of 50 is going to be somewhere between 7 and 8, because 7 squared is 49, 8 squared is 64. So my guess is that we're going to get a final velocity here, or a final speed of like 7 point something. And it turns out we get 7.20 meters per second. And that's the conclusion of this problem. Once again, it was helpful to draw a little picture. Remember, for conservative forces, the actual path or the shape of this slide doesn't matter. Like I said, you could have bumps in it. You could actually make the slide go down, put a loop in it, and then reach the bottom. As long as that top to bottom is 2.61, as this problem dictated, it doesn't matter the path. Once we had that picture, we wrote out our equation. Note we completely neglected the springs here because there are no springs in this problem. We set a reference position to be the bottom here so we can get rid of our final potential energy due to gravity. And then once we put in numbers, we were just able to algebraically solve. Okay? So once again, nothing too crazy about these. In upcoming videos, we'll be taking a look at some more of these problems for conservative forces, and then we're going to start looking into examples where we do include friction and some work is done on our object. But until then, this problem is finished. Adios, and take it easy.